You're listening to AI Podcast. I'm Daniel, and today we're unpacking an ACL 2025 paper titled Gödel Agent, a self-referential agent framework for recursively self-improvement.
I'm Maya. Give me the headline first. What's the one-line takeaway?
TLDR, Gödel. Agent is an AI system that can read and rewrite parts of its own running code, then test those edits and keep what works. In controlled evaluations, it generally beats strong hand-designed and automated design baselines, and in an open setting, it can even decide to call a stronger external model when that helps.
So it's an agent that edits itself while it's running. Who led the work?
The lead author is Xunjian, with collaborators including Xinyi Wang and Yang Wang. The affiliations span Peking University and UC Santa Barbara, with a collaborator from the University of Arizona.
All right, what problem are they trying to solve?
Most agent systems fall into two camps. First, hand-designed pipelines that are powerful but basically fixed once deployed. Second, meta-learning approaches that can tune prompts or modules but still follow a human-specified routine. Both restrict the search space of possible agent designs. Gödel Agent aims to remove those limits by letting the agent change not just its policy, but also the way it improves that policy.
Meaning it can change how it changes itself.
Exactly. The design is self-referential, inspired by the Gödel machine idea. Concretely, the agent can inspect its own code in runtime memory and monkey patch replacements. It then evaluates the new logic and keeps improving. Alongside that, it uses practical scaffolding like thinking before acting and explicit error handling so it can back out of bad edits.
How is this different from other self-refined systems we've seen?
Two key differences. First, the improvement target is the code of the agent itself, including the loop that performs the improvement. Second, the decision process is recursive. At each step, it can analyze, interact with the task for feedback, inspect itself, and self-modify. There are also utilities like calling an LLM, running code, and handling errors as part of the toolkit.
Got it. What did they test it on?
4 established benchmarks that stress different skills: DROP for reading comprehension, MGSM for math reasoning, MMLU for broad knowledge and reasoning, and GPQA for graduate-level science. They start each domain with a simple chain-of-thought policy, then run 6 independent self-improvement cycles with up to 30 iterations per cycle on validation data. The final agent is evaluated on a held-out test set.
And the model power is held constant when they compare against baselines?
Yes, for the main constrained comparison, all tests are run with GPT 3.5 for both baselines and the optimized agent. During the self-improvement process, the agent may use a stronger model to think and plan, and later they also report an unconstrained setting where the agent can freely request help from more capable models.
Okay, results. How did it do?
Under the same constraints, Gödel agent matches or surpasses a recent automated design baseline called meta-agent search across the board. On the math benchmark, MGSM, it improves by about 11 points. In the unconstrained setting, performance climbs further because the agent sometimes chooses to consult a stronger model. The authors argue that this is the point of open-ended autonomy. Learn to use the tools available when the budget allows.
Interesting. Do they say what actually drove the gains?
Their ablations suggest that planning and recovery matter most. Removing the think-before-acting step or the error-handling mechanism hurts results the most in their math tests, while removing code execution or direct LLM to LLM calls has a smaller effect. Logs show the agent often analyzes, interacts for feedback, and then self-modifies, with error handling showing up frequently in practice.
Does it ever make a mess of itself when it rewrites code?
It can. The paper notes that unexpected terminations are rare, but temporary dips in performance happen as the agent explores changes. The system usually recovers because it can revert or adjust after errors, which is exactly why the error handling and rollback logic is there.
Any concrete example of that self-referential behavior paying off?
Yes, a case study on the game of 24. The agent begins with an LLM-only solver and struggles. It then rewrites itself into a search-based solver and reaches strong accuracy. It's a clean example of abandoning a pure prompting strategy and adopting a new algorithmic structure when the data suggests it.
And cost-wise, this sounds like it could be pricey.
Surprisingly manageable in their setup. A full evolution across the 4 benchmarks, with up to 30 self-improvement iterations, costs on the order of $15 in API usage, which they contrast with a few $100s for a meta-agent baseline. Faster convergence and controlled validation runs help keep costs down.
What are the caveats?
2 big ones. First, self-improvement is guided by validation feedback on relatively small splits, then tested once on a disjoint test set. That's standard, but it raises the usual questions about overfitting to a particular validation slice. Second, in the unconstrained setting, part of the improvement comes from escalating to a stronger model. That's a useful capability result, but it mixes algorithmic progress with model choice. The constrained comparisons are the cleanest test of the method itself.
And what about safety? An agent that can rewrite its own code sounds powerful.
The authors recommend practical guardrails, sandboxed execution, constrained scopes for what can be changed, strict audit logs, and rollbacks. In real deployments, you'd want strong monitoring and policy checks around the self-modification loop.
All right, wrap it up for builders listening today.
Gödel agent shows that giving an AI controlled access to introspect and edit its own code can yield general cross-domain gains without heavy domain-specific engineering. It's flexible, relatively cost-efficient in their setup, and it highlights which scaffolds really matter: careful planning and robust error recovery. Next steps include broader generalization tests, longer horizon tasks with richer tool use, budget-aware decisions about when to escalate to bigger models, theory for convergence, and stronger safety scaffolding.
Nicely put. Quick reminder on the authors and venue before we close.
Led by Xunjian with collaborators including Xinyi Wang and Yang Wang, appearing at ACL 2025.
That's it for today's AI podcast. Thanks for listening, and we'll see you next time.